In our final hypothesis test of the mean, when the population standard deviation is known, we'll do a two-tailed test. During a particular week, 13 babies were born in a maternity unit. Part of the standard procedure is to measure the length of the baby. Given below is the list of lengths in centimeters of the 13 babies born. Assuming the sample came from a population with a normal distribution that has a standard deviation of 3.0 centimeters, test the claim that the population mean length of the babies is 50 centimeters. Use a 0.05 significance level. Okay, so we're going to have the raw data. Let's scroll down and see that. So there are the 13 lengths from the babies. And we have a normal distributed population with a standard deviation of 3 centimeters. So let's make a note of that. So sigma is equal to 3.0. And our test is a claim that the length is 50 centimeters, is implying the equal sign. We'll use an alpha of 0.05. Okay, original claim. The mean is 50 centimeters. The competing claim. So we have to cover all other possibilities. Mean is 50, so we would want everything less than 50, everything greater than 50, and the way we say that is it's not 50. The mean is not equal to 50 centimeters. So our null hypothesis, of course, is the mean is 50 centimeters. And our alternate hypothesis corresponds then to the competing claim, that the mean is not 50 centimeters. You'll hear the words is different from. It could be lower, it could be higher, but it's different from 50 centimeters. Okay, we will get our critical value, a test statistic, p-value. We'll draw a decision diagram, we'll make a decision. Okay, so let's get the diagram started. This time our alternate hypothesis tells us we have a two-tailed test. Where the area on either tail is alpha over 2. We have to split our alpha. We said alpha is 0.05, so we'll have 0.025 on the right and alpha over 2, or 0.025 here on the left. So to get the critical values, of course, we know with our symmetric graph, we know that whatever the value is here, it will be negative, and this will be the opposite of that, the positive of that number on this side. So we really just have to calculate one of them, and this is the easy one because we want to put an area to the left and we know exactly what that is. Okay, inverse norm. Go to our distributions, inverse norm, area to the left, 0.025. And this is the common critical value of negative 1.96. Let's click that. Okay. Negative 1.96. But now we know we have, let me change the color here. So this is negative 1.96, and that means this is positive 1.96. And so our Z critical value plus or minus 1.96. We have 2, so that's how we can indicate that, with the plus or minus. Okay, now we need to run our Z test. We had raw data again, So we'll enter this data in the calculator in a list. Stat, edit, that's where we enter in data in a list. Okay, we have 49, 50, 45, 51, 47, 49, 48, 54, 53, 55, 45, 50, and the last one was 48. That was my 13th data value, and now I've got all of my data in a list. So then we'll say stat tests, and this is the z-test. Sigma is known, mean, sigma known, z-test, enter, and we have data. My mean at the null hypothesis is 50, so I'll tab down and type in 50. Our population standard deviation was given to be 3 or 3.0. I can put 3.0 in there. The list was in list 1. The frequency is always on 1. If that ever gets changed, just type a 1 back in there because it needs to be 1. And this was a two-tailed test, so that's highlighted there. Then I want to calculate. Okay, my test statistic is z equals -0.55 rounded to 2 decimal places. My p-value rounded to 4 will be 0.5791. You see the 5th decimal place is a 9, so that'll round this 4th one up to a 1. 0.5791. So test statistic z equals -0.55, and my p-value 0.5791. Okay, so we're here at -0.55. And this p-value is actually greater than 50%, 0.5. So we can tell that what we're seeing is this area here as our p-value. 0.5 would be at the mean, right? So our decision, is the test statistic in the critical region? No, it's not. Is the p-value greater than alpha? Much, much greater. So we fail to reject HO. Okay, all we have left now is the conclusion. Does the original claim contain the condition of equality? Yes, it does. That means the original claim and the null hypothesis correspond. So our decision about the null hypothesis will be the same decision about the claim. And then the next question is, did we reject? No, we did not. We failed to reject. So our conclusion, there is not sufficient evidence to reject the claim that the population mean length of the babies is 50 centimeters. So we see that because these two correspond, we do not have evidence that we can reject the null hypothesis. Therefore, we do not have evidence to reject the claim.